Now, in the first part of this lesson, we have started by studying this function in order to eventually graph it. Now, in the first part, we have started by determining particular points of this function, which are the x and the y intercepts. And then in the second part, we have studied the variations of the function, and we ended up setting up its table of variation over the given domain 0 to pi, where we actually studied the variation of the function using the first derivative. Now, in this second part, we're going to continue our study of this particular function by now studying the concavity of the function, because now that we know here, for example, that the function is decreasing than increasing over this interval, but however, a decreasing function could be decreasing either concave up or down. So the concavity of the function is in fact determined by the sign of the second derivative of the function. So almost the same process that we followed here in order to study the variation of the function and set up its table of variation, we're going to do a similar work but with a second derivative, because in a previous lesson we have studied how the concavity of the function is affected by the second derivative. So here for part C, I'm going to start by finding the second derivative of the function, which is the derivative of f prime here. So negative sine has a derivative of negative cosine, and negative cosine has a derivative of positive sine because cosine has negative sine as its derivative, so it's plus sine x. So now that we have the second derivative, similarly, the second step in order to set up a table of concavity would be to find the roots of the second derivative. So over here, I need to start by finding the roots of f double prime. So the roots of f double prime would consist of solving the equation f double prime equals to 0. However, f double prime equals to 0 would lead me to cosine equals to sine, which is the same equation that we actually solved here when we were determining the x-intercept of the function. So here, since we've already solved this equation, we're not going to solve it again. However, we're going to just admit the roots, which are pi over 4 and 5 pi over 4, of course, over the domain 0 to pi. So here, that would give me x equals to pi over 4, or x equals to 5 pi over 4. Now that I have the roots of the second derivative, I start by setting up the table of concavity of the function. So again, the first row would be a row for x, which would include the domain of the function, the domain we're working on, in addition to any restricted values if they existed, but however here the function does not have any restricted values. And we'd also include the roots of the second derivative. Since this is a table of concavity, we need to include the roots of the second derivative. So the second row would be a table of signs of the second derivative f double prime, because the sign of f double prime really affects the concavity of the function, and this is a table of concavity, so we'd have to really study the sign of f double prime here. So we already know that f double prime is 0 at pi over 4 and at 5 pi over 4. Now, similarly to how we determined the sign of f prime here when we were setting up the table of variations by just testing f prime at particular points over the interval, over each interval, we'd basically do the same thing here by just choosing random points inside each interval and just evaluate the second derivative at those points, you'd actually be able to determine the sign of f double prime over each interval. Now over here, by doing that, between 0 and pi over 4, the second derivative would be negative. Then over the second interval it would be positive. Then between 5 pi over 4 and 2 pi it would be negative again. Now for f of x, since this is a table of concavity of f, in that case we'd need in the last row to show the concavity of the function, whether it's concave up or it's concave down. Now we do know that when the second derivative is negative, the function would actually be concave down. When the second derivative is negative, it means that over that interval the function has a maximum. Now over here, the second derivative being positive, so the function would in fact be concave up. And again here, concave down, since the second derivative is negative. Now the question does ask for the inflection points. Now by definition, points of inflections are the points where the function changes concavity. So you'd notice that here it's concave down, then concave up. So at pi over 4, the function did change concavity. So we have a point of inflection here. And similarly, at 5 pi over 4, we'd notice that the function did undergo a change of concavity, so we also have a point of inflection there. So you'd notice that to answer our question, that f is concave up over the interval where it's concave up, that's pi over 4 to 5 pi over 4, and f is concave down, and that's over. Now you'd notice it's concave up, concave down, sorry, over 2 intervals, so we just consider the union of these 2 intervals. Okay, and now finally, the function does have 2 points of inflection, so points of inflection would actually be, by the way, these are the roots of the function according to part A. This is where the function admits x-intercepts, so we already know the y value to these values of x is 0. So that's pi over 4, 0, and 5 pi over 4, 0. So now that we've set up the table of concavity and we already have the table of variations in addition to the intercepts of the curve, now we can start by just sketching the curve. So over here, let me just open this new page in order to have enough space. Let me just redo that. So over here, we need to graph the function over 0 to pi. So this is why we don't need the negative side of the x-axis anyway. So I'm going to go by a scale of pi over 2 at the x-axis, and then with this scale for 1 on the y-axis. So we do know, according to part 1, that the curve admits a y-intercept at 0, 1. So that is in fact this point here. And we also know that at pi over 4 and 5 pi over 4, the curve does admit 2 x-intercepts, which are also the points of inflection of the curve, which are pi over 4, 0, and 5 pi over 4, 0. So if this is pi over 2, then pi over 4 is halfway between 0 and pi over 2. And 5 pi over 4. Now 5 pi over 4 is pi plus pi over 4, which would basically be here. Now, we've just plotted the points of inflection, which are also the x-intercepts, and we've also plotted the y-intercept. Now, going back to where we studied the variation of the function, we know that the function has a maximum and a minimum at 7 pi over 4 square root 2 and 3 pi over 4 minus square root of 2. Now, 3 pi over 4 would actually be here. It would be pi over 4 after pi over 2 or before pi. So it's halfway between pi over 2 and pi. So that is 3 pi over 4. And it has a y value of a square root of 2 or negative square root 2. Which one is negative? So 3 pi over 4 is negative square root of 2. Negative square root of 2 is around 1.41, so that's almost halfway between negative 1 and 2. So that is the point we are actually looking for, and keep in mind that this is a minimum. So being a minimum, it means that the curve admits a horizontal tangent there. So similarly, the other extrema is a maximum at 7 pi over 4. Now 7 pi over 4 is 2 pi minus pi over 4, so it's right here halfway between 3 pi over 2 and 2 pi, with an ordinate of square root of 2, which is almost 1.4, so that is almost here approximately. Of course, with a grid it'll be more accurate. So, of course, over here, we'd have to point out that the curve admits a horizontal tangent there, because at that point, the curve has a maximum. So these are the points that we'd actually have to go through. Now, I did mark this one, but this one is the abscissa of the minimum I have here. So disregard this one when we're graphing. So usually I prefer, whenever I'm graphing, I prefer to actually start with extrema points. So I know that between 0 and this point, which was 3 pi over 4, that the curve is in fact decreasing. It's decreasing, and the function is concave down here, then concave up after the point of inflection at pi over 4. So over here, the curve would actually so don't forget that it has to be really smooth, admitting a horizontal tangent here. So now that I've drawn this part of the curve, I have another horizontal tangent here where the curve would still be increasing while concave down. And at 2 pi, the y value was 1, so we'd have to stop it here. And that is the curve relative to f of x. So if we were to recap a bit, so in order to be able to study this function, starting from its domain all the way to its graph, so what we did is we started by setting up or determining particular values of the function, which are the intercepts. Then we studied the variation of the function over 0 to pi, the domain given, in order to determine the sense of variation of the function, where the function is increasing, where it's decreasing, and determine where it has a local maximum and local minimum. And finally, we did use the second derivative in order to set up a table of concavity of the function to help us determine where the function is concave up and where it's concave down, in addition to finding the points of inflection of the curve. And all of that together helped me eventually sketch this function.